Hey everyone, and welcome to the deep dive. We're diving into a super fascinating topic today: memory-centric computing.
Yeah. This one has the potential to completely revolutionize how computers work.
We've got a ton of sources to work with today, from academic papers to industry articles, and we're going to break them down for you.
Sounds good.
Our goal today is to help you understand what exactly memory-centric computing is, why it's causing so much buzz, and what its future might look like.
It's a pretty big deal.
So imagine a world with crazy fast devices and batteries that last for days.
That's the kind of future we're talking about. It's a total game changer. For so long, we've relied on processor-centric computing.
Right.
And it's possible that that approach is actually holding us back.
Okay, so when you say processor-centric computing, you mean the way computers work now, right?
Correct.
What exactly is the issue with that?
The main problem is that data is constantly being shuffled back and forth between the memory, where it's stored, and the processors, where the computations actually happen. Think of it like a chef who has to run to the pantry every time they need an ingredient for a recipe, instead of just having everything prepped and ready to go.
Okay, I get it. So all that data movement, that constant back and forth, it takes a lot of time and energy.
Exactly. And it limits how fast and efficient our computers can be.
So basically the processor's like, give me that data, and the memory's all, hold on, I'm coming, and everything just grinds to a halt.
Pretty much. But that's where memory-centric computing comes in and completely shakes things up.
Yeah. How so?
Instead of moving the data to the processor all the time, we're essentially bringing the processing power to the data.
That's smart. Much less running around, a lot more getting things done. But how do we actually do that? How do we bring the processing power to the data?
There are two main approaches that are being explored right now.
Okay.
The first one is called processing using memory, or POOM.
POOM.
With POOM, we're actually performing computations directly within the memory cells themselves.
Wait, hold on a sec. You're saying that the memory can do calculations? How is that even possible?
It's really cool. It involves using the physical properties of those memory cells to perform calculations without actually moving the data out.
Wow.
So, for example, picture a row of data in DRAM. We could perform a calculation on that entire row simultaneously by manipulating the electrical charges within those cells.
You're kind of blowing my mind right now, so it's almost like doing math with electricity.
It kind of is. It can be unbelievably fast and efficient because you're cutting out all that data transfer time.
Yeah, that makes a lot of sense.
In fact, one research team even used this approach to generate random numbers right inside the DRAM.
No way. So the memory isn't just storing data, it's actually crunching numbers too.
Yeah.
That's PEWM, right? What about the other approach you mentioned?
Right, so the second approach is called processing near memory, or PNM.
PNM.
Remember that analogy of mini kitchens right next to the pantry?
Yeah, I remember.
It's a good way to think about PNM. We're essentially placing processing units very close to the memory so the data doesn't have to travel as far.
So less travel time for data equals faster processing. Makes sense. What would that actually look like in a real computer, though?
One good example is something called 3D stacked memory. Instead of laying memory chips out flat on a circuit board, we're stacking them vertically, kind of like a high-rise building for computer chips. And we can integrate those processing units right between the layers.
Oh, okay. So the processors basically have a direct line to the memory they need.
Yep. No more long commutes for the data.
That's really clever. Are companies actually making hardware like this?
They are, and it's a really exciting area of development right now. Companies like Samsung and Intel are investing a lot in 3D stacked memory. And they're even designing specialized processors that are specifically optimized for certain tasks, like AI workloads.
So we've got memory and processing power working together in a totally new way. It all sounds pretty incredible, but it makes me wonder, if this technology is so amazing, why isn't it already in every single computer?
Well, it's a pretty big shift, and there are definitely some challenges that need to be addressed. Well, one of the biggest hurdles is programming complexity. We need totally new tools and strategies for developers to be able to write software that can take full advantage of these memory-centric architectures.
So it's not just a matter of plugging in new hardware and expecting everything to work perfectly. The software needs to catch up too.
Yeah, exactly. It's a totally different way of thinking about how to design software.
Got it.
And then there's the challenge of actually integrating these new processing units into our existing computer systems. We need to make sure that everything works together seamlessly, that data is handled correctly, and that nothing gets lost or corrupted in the process.
Right, because what's the point of making things faster if we're just going to lose data along the way?
Exactly. Security is another big one too. With processing happening closer to the data, We need to be extra careful about protecting sensitive information.
Makes sense. And I imagine new technology is always pretty expensive at first, right?
It is. Bringing down the cost of memory-centric computing is going to be key if we want it to become widely adopted.
Yeah, I mean, think about any new gadget. It's always super pricey when it first hits the market,
Yeah.
but then the price usually comes down over
Yeah,
time.
exactly. But even with these challenges, there's a ton of excitement surrounding the potential of memory-centric computing.
I can see why.
We're potentially talking about massive improvements in performance and energy efficiency. Think faster devices and way longer battery life.
Now, that's something I think we can all get behind.
Absolutely. And it goes way beyond just faster phones and laptops. Memory-centric computing could have a huge impact on fields like artificial intelligence and data analytics.
Really?
It could even help us address some of the environmental concerns we have by reducing the energy consumption of massive data centers.
Wow. So it really could change the world in a lot of ways. But we're still early in the game, right? There's a lot to figure out.
Oh yeah, we've only just scratched the surface. There are a ton of researchers out there exploring new materials, new architectures, and new ways to program memory-centric systems.
It sounds like we're on the verge of a pretty big tech revolution.
I think so.
Well, we've covered a lot of ground in this first part of our deep dive. We've talked about what memory-centric computing is, why it's such a big deal, and some of the challenges and opportunities it presents. Ready to dig a little deeper?
Absolutely. Let's do it.
Great. We'll be right back to take a closer look at the technical details of those two main approaches. PAM and PNM. Don't go anywhere.
Sounds good.
All right, welcome back. We just laid out the big picture of memory-centric computing, and now it's time to zoom in on the more technical side of things.
That's good.
Okay, so we talked about two main approaches: processing, using memory, or PAM, and processing near memory, PNM.
Right.
Let's try to unpack those a bit more, starting with PM.
Okay.
You mentioned earlier that PM involves actually doing computations inside those memory cells themselves.
Yeah.
That sounds kind of wild to me.
It is pretty revolutionary. To really understand how it works, it helps to picture DRAM,
Okay, DRAM.
which is the most common type of memory in computers.
Great.
Each DRAM cell stores data as an electrical charge, kind of like a tiny little battery.
Okay.
Now imagine we could manipulate those charges to do math right there in the cell itself, without having to move that data around.
So the memory cells are basically acting like tiny calculators.
Exactly.
What kinds of calculations can they actually perform?
Well, we can do things like bitwise and data operations across an entire row of DRAM cells at the same time.
Wow.
It's incredible, and it all comes down to cleverly adjusting those voltages within the memory array. And because we're cutting out all that data travel time, the speed is amazing.
Yeah, that makes sense. No more waiting for data to be fetched. It's all happening right where it's stored.
Hmm.
Are there any real-world examples of PUM in action?
Oh yeah, definitely.
Really?
Researchers at ETH Zurich, they've developed something called DRange, which is a DRAM-based random number generator.
Range.
Yeah. They figured out how to use the inherent randomness in DRAM cells to actually generate really high-quality random numbers directly on the memory chip.
So the memory itself becomes a source of randomness. That's pretty mind-blowing. Okay, so that's PM. Let's move on to PNM, processing near memory.
Okay.
I remember we were talking about the analogy of mini kitchens next to the pantry,
Right.
but what are some actual examples of PNM being used in computers?
One of the coolest and most exciting developments is 3D stacked memory.
3D stacked memory.
So instead of having those memory chips laid out flat on a circuit board, we're stacking them vertically, like layers on top of each other.
Okay.
And we can actually put processing units right in between those layers.
So the processors have super fast access to the memory above and below them?
Exactly.
No more long-distance data commutes? Are companies actually building these 3D stacked chips?
Oh yeah, it's a really hot area of development right now. Companies like Samsung, Intel, and SK Hynix are all investing in this tech. They're even making specialized processors that are designed to speed up particular tasks, like AI workloads.
So it's not just about general processing, it's about customizing hardware for specific jobs. This is all super impressive. But I have to ask, if it's so revolutionary, why isn't it already in every computer out there?
Well, it's a huge change. And there are still some obstacles we need to overcome.
What kinds of obstacles?
One of the biggest is programming complexity.
Yeah.
We need totally new tools and strategies to help developers write software that can really take advantage of these memory-centric architectures.
Right, because it's not like we can just run our existing code on this new hardware and expect everything to work flawlessly.
Exactly. It requires a whole new way of thinking about software design.
I see.
Another big challenge is how to effectively integrate these new processing units into our current computer systems. It's got to be seamless.
Right.
We need to make sure the data is handled correctly and that we're not losing or corrupting anything in the process.
That makes sense, because what's the point of having blazing fast processing if we're just going to end up with errors and data loss?
Oh. Exactly. And we can't forget about security. With processing happening closer to the data, we need to make absolutely sure that sensitive information stays protected.
Of course. So how do we tackle those challenges?
Well, researchers and engineers are working on a lot of different solutions. We need clear communication protocols and ways to ensure that all the processing units, both in the memory and in the main processor, are synchronized.
So it's kind of like making sure all the cooks in those mini kitchens are on the same page and not bumping into each other or messing up the dishes.
That's a great analogy. We need to avoid situations where processors are working with outdated info or conflicting instructions.
It sounds like there are some really tricky problems to solve.
There are, but the potential benefits are so big that finding solutions is definitely worth it. I mean, we're talking about computers that could be like orders of magnitude faster and way more energy efficient.
Faster phones, longer battery life, more powerful AI. It sounds almost like something out of a sci-fi movie.
It really does.
Yeah.
And the best part is, it's actually happening. We're on the cusp of a huge transformation in the world of computing. And that's not even mentioning the potential impacts on things like data analytics, scientific research, and even sustainability. We'll dive into those aspects in a bit.
Sounds good.
But first, I think it's worth taking a closer look at some of the specific research efforts that are underway to address those challenges we just talked about.
Okay, let's do it. Let's see what the brilliant minds working on this stuff are up to. So we've talked about the what and the how of memory-centric computing, but now I'm curious about the who. Who are the big players actually making this whole revolution happen?
Oh, it's a really exciting mix of people. You've got researchers from all these universities, engineers at big tech companies and startups. They're all pushing the boundaries of what's possible.
So it's not just one company or one lab leading the charge?
Not at all. It's a global effort. There are these incredible research groups at places like ETH, Zurich,
Okay.
Stanford, and MIT. They're doing groundbreaking work on both the hardware and the software.
Right.
They're publishing papers, they're going to conferences, and they're working directly with companies to take their ideas and turn them into real products.
So it sounds like the universities are really laying the foundation, coming up with the big ideas and then proving that they can actually work.
Yeah.
What about the tech companies? What role are they playing in all this?
Well, the big companies, the Samsungs, the Intels, the SK Hynixes of the world,
Right.
they have the resources, they have the expertise to take these cutting-edge technologies and manufacture them at scale.
Right.
They're the ones who can turn prototypes into products that we can actually use.
So they're turning it into something real. And you mentioned startups, too. What are they up to?
Well, the startup scene is just buzzing with activity right now. But tons of these innovative companies popping up, and they each kind of focus on a specific area of memory-centric computing.
Okay.
Some of them are developing these very specialized processors that are designed for certain tasks,
Yeah.
and others are creating software tools that make it easier for developers to build memory-centric applications.
So we've got the universities generating the big ideas. We've got the big companies building the hardware. And then we've got the startups kind of filling in the gaps with these specialized solutions. It sounds like a pretty dynamic ecosystem.
It is. It's really exciting, and all of that collaboration is what's really going to drive this technology forward.
This has been a real journey for me, this whole deep dive. I mean, memory-centric computing is clearly a game changer, and it's so cool to think about all the ways that it could make things better. But as we wrap up, I'm wondering if there are any potential downsides or challenges that we need to think about as this technology starts to become more widespread.
Yeah, that's a really important point. I mean, the benefits are huge, but we do need to consider the broader implications.
Right.
So, for instance, as memory-centric computing makes AI and automation even more powerful, we have to think about how that's going to impact jobs in various industries.
That's a valid concern. I mean, we've already seen how automation has led to job displacement in certain sectors.
Exactly. So we need to start thinking now about how we prepare the workforce for these kinds of changes, maybe through things like retraining programs or educational initiatives.
Yeah, that makes sense.
Another thing to be aware of is access and affordability. We want to make sure that this technology benefits everyone, not just a select few.
Right. We don't want a situation where only wealthy or privileged people have access to the most powerful tech.
Exactly. So it's not just about the technical aspects of memory-centric computing, it's also about these bigger societal questions.
Yeah, it really sounds like there's a lot to think about here.
There is. As with any powerful technology, it's up to us to use it wisely and ethically. We have to have these conversations about the potential impacts and work together to make sure that this technology benefits society as a whole.
Well said. This deep dive has been a real eye-opener for me, and I'm sure for our listeners too. We've covered everything from the fundamental concepts to the potential impacts on society. Any final thoughts you want to leave our listeners with?
If I had to sum it up, I'd say the future of computing is in memory. Keep an eye on this space, because it's going to be an amazing ride.
Couldn't agree more. It's been an amazing exploration. Thanks for joining us on this deep dive into the world of memory-centric computing. Until next time, keep learning and keep exploring.